Today we are going to start something called a relative motion. So before we start this chapter, numerically or equation wise, we need to understand that why we are studying this chapter. What is the motivation behind learning this particular chapter? Okay. So unless we will not understand the motivation, it's meaningless to learn this chapter, to study the formulae. So now in physics, we have talked about, I might not have said before also, something called, there are two types of frame, inertial and non-inertial frame. Okay. So we have types of frames. So let's talk about the types of frames. So I haven't talked. Now, what are frames? So as the name says, frame is a framework. Just like in software, we have frameworks. So these are the ways in which we handle the situation. Like so, situation means like any physical event we try to observe. So that's called physical event. So when we have some event, then we try to observe, and to observe the event, we need to have some framework. So we call it frame of reference, like from the where the observer is watching the entire event. And we have two types of references in physics. One is called the inertial frame of reference, and I will talk about what is this. And the other is called non-inertial frame of reference. So we have two types of reference, inertial and non-inertial. Now, these two types refers to something. So let's say you're trying to observe a phenomena standing on the Earth's surface. So basically, you are at rest, or maybe you're trying to observe the phenomena not from the ground, but in a moving vehicle. So let's say you happen to be in a bus, and the bus is heading in one particular direction on a horizontal road, and the driver is driving the bus with constant velocity. So the idea is, if the driver is driving the bus with constant velocity, then such frame is maintaining the inertia, because if you maintain your velocity, so your state is maintained. So we say that such frame maintain the inertia. So being at rest or moving with constant velocity refers to inertial frame of reference. And for the obvious reason, because inertia refers to inertia. So if you maintain your inertia, you are in the inertial frame of reference. But if you start turning or start accelerating, then you change your inertia. So if you are in a like a frame, or you can think of a bus or vehicle which keeps on turning, which keeps on accelerating. So such frames we call non-inertial frame of reference. Okay. So there are two things that we need to understand. One is called the inertial frame, and that's called the non-inertial frame. So what is inertial frame? Athar, are you there listening to me?
Yes, sir.
So what is inertial frame? It is a frame which either remains at rest or moves with constant velocity. So any frame which is either at rest or moving with constant velocity, we call it inertial frame of reference, because inertial refers to the word inertia, and inertia means to maintain the state of motion. So if you choose a frame, or you can say some setup, observational setup you can think of. So if you choose a frame or some observational setup to observe a physical event such that that setup is either at rest on the earth or it is moving with constant velocity relative to earth. In both cases, the setup, the frame, or the coordinate system that we choose, we call inertial frame of reference. So for rest of the cases, we call it non-inertial frame. So we say that any rotating or accelerating frame is called non-inertial frame of reference. Okay. So these are the frames. We have two types of frame, inertial and non-inertial. And what is important is to understand that these are the basically observational setups in which, or like I mean, when you observe something, you will be either of the two setup. Like you cannot be in the third setup. So any observer, when observes some event, he must be either in the inertial frame or non-inertial frame. Okay, now that's done. The second thing, even the inertial frame can have variety of velocity. So we can have infinite number of inertial frame in which every frame will have different velocity, or some may be at rest, some may be in motion. But as long as the velocity are constant, all are inertial. So only when the velocity vector changes, we call it non-inertial frame. So for example, let's say if you are standing uh, near a road, you are looking at a infinite number of vehicles, uh, crossing your eye. So all observation which you're making there, you have become an inertial frame. Why? Because you're standing still. Now, let's say you are one of the driver among the whole vehicles moving on the traffic. So you're one of the driver, and now you start observing other drivers. And let's say your car is moving with constant velocity. So now imagine yourself at the driver's seat, looking at the surrounding cars, right, left. So another car is coming from the right of you and maintaining its velocity exactly same as you. What you will see, the other driver in motion or at rest. So there is a parallel car to your car having exactly same velocity as your car. So what will you say, the other driver or the other car, motion or at rest?
So at rest.
Yes, you must say at rest. It is not about you know that it's moving. No, in physics, that will not be called the right observation. So we know that the car is moving, but what we are observing that the car is at rest in my frame. So you as a driver, when you observe some other car, then what you see is your observation. And every observer is supposed to stick to their own observation. So if your car is moving faster than most of the car, then in your frame, what will be the velocity of each car? Imagine you are the fastest guy on the road. So for you, every other car is moving along your direction or opposite to your direction.
or opposite.
Exactly. So every other car is going backward. Why? Because the gap is increasing always. So in your frame, the velocity of each car is backward. So now your observation is something which you are seeing. So you must stick to your own observation and analyze accordingly. So motion cannot be absolute. Motion is always a relative concept, and the concept, the notion of motion comes from the observer or the frame of reference. So we write the kinematical equation as per our own observation. That is the truth. So we do not write in the ground frame, we write in our own frame. So what I see is what I believe. Okay. So relative motion is the inherent part of any physical phenomena. So when we have some motion happening, a relative motion will come automatically. I mean, it is not something that I need to invoke. Okay. And the observer must be in either of the two frames which I just discussed, the inertial frame or non-inertial frame. Let's say you have a car and you accelerate your car. Okay. So can we see the acceleration or can we see the displacement?
So we can
What?
see the displacement.
Yeah. So there are just two physical entities that you can measure in real time. One, the time interval, which you can measure using the stopwatch or any timepiece. And the second observation that we can make is called displacement. And using these two information, we try to evaluate the other physical quantity. So let's say you make an interval of 0.1 second and you get some displacement. So you take multiple intervals of 0.1, 0.1, 0.1, 0.1, 0.1, and then you find ds, 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 every interval. And what do you see that every time when you're measuring a ds, it is coming to be same. So if it is coming out of same, coming same in each calculation, it means your velocity is constant or variable. So if you are traveling equal displacement in equal time interval, however small is the time interval, then what we can say about your motion?
Sir, it is
Uniform.
uniform.
Exactly. So the uniform motion is coming from this fact that every interval which I have taken, the equal interval, every equal interval I have taken, and irrespective of the size of the interval, what I'm finding is that in equal interval we have equal displacement, and so I must say that it is uniform. But now imagine if the ds is increasing in every interval. Interval is same, but ds is increasing. So we can say the speed is changing. And if the speed is changing, then we must say it's a accelerating object. And if it is accelerating object, So if you are in a frame which is accelerating, we call it non-inertial frame of reference. So it's a very technical terms like inertial frame of reference, non-inertial, but it's really easy to understand. What you need to realize that which frame you are in and trying to observe the event. Now we need to understand again one thing which we have just discussed. There are only two observable quantities in physics when it comes to motion. So there are just two observable quantities. So we can just observe two things. One is the time, and other is the
Displacement.
what? Displacement. Now displacement is something which varies from frame to frame. Okay, so for example, if you're driving car and if there is another car which is driving beside you, so you can see that you both are traveling in the same direction with the same speed. So for you, there is no displacement for the car. So you can say that okay, the car is not displacing at all. Why? Because you always see the car on the right of you. But if I think that you are standing on the road and observing the same car, then as the time will progress, the car will go ahead. So there will be some displacement. So what we need to realize that displacement is a frame dependent entity. It means there is no absolute value of displacement unless the frame is not specified. So the moment you specify the frame, then the calculation begins. And it is a very common observation that every frame will give you or may give you, not definitely. So every frame may give you different answer. So the displacement varies from frame to frame. So now let me put the two big factors like displacement and time interval. I will not say time. Now time is something which we don't measure. Can we measure time?
So we can measure interval.
Yeah, we can only measure interval. Time is immeasurable. So what is the time now? We can't say. Okay. So you may say no, sir, it's 8:38 a.m. Okay, no, I'm saying the absolute time. Since the Big Bang, universe came into being, and from there till now, what is the time? We have no idea. So every clock or timepiece gives you some number so that you can compare the previous and the present number, and then you can calculate the interval. The idea is these are a repeating phenomena called periodic motion. So all time devices works on some periodicity. So these periodicities are either created mechanically or it is natural. For example, the motion of satellites, like natural satellites around the planet, it's a natural periodic motion. Motion of planets around the sun, it's a natural periodic motion. So time always depends on some sort of periodicity in order to calculate. And since time immemorial, we have been using the various periodic motion in nature to develop the notion of time interval. So earlier, like the Hindu calendar, or in fact, most of the Asian calendars are made with the lunar cycle. So we have something called lunar calendar, in which we observe the motion of moon to decide the duration. And it is found that the roughly moon takes 27 days and few hours to complete the Earth's rotation. And therefore, roughly we call it 28 days or 4 weeks or 2 fortnights, and divide the lunar cycle, sorry, the lunar cycle into two subparts. So out of 28 days, the first 14 days you can say no moon, and then we say full moon, and in Hindi we call Amavasya and Purnima. So those things are always in place. So these are basically the measurement of time. Like these are like old ancient, you can say, method to measure the time. And because in one Gregorian calendar we have 52 weeks, which amounts to 13 lunar months, like the Hindi month, the Shravan is going on, and then Bhadra will come and so on. So these all are time measurements, and there is a beautiful history of time. I mean, if you have some time, then okay, it's nice. You can study about it. So now displacement time interval are only measurable quantities. And now I am particularly interested in the second term. So my interest lies here. And why it lies here? Because it is something very, very interesting. I mean, we need to figure it out why I'm saying so interesting. So time interval is something unique, difficult to realize at first, but it is unique. Why? So let's say you're making some event. Now tell me, whatever you observe, like let's say the two cars are colliding. So that can be observed by a person standing on the road, or maybe a person in the car, or maybe person flying in the helicopter. What do you think? When the car will hit it, are they going to observe at the same instant or at different instant? So there are various observer I have just, pointed out. So my question is, if some event occurs in nature, will it be occurring at different instant of time for each observer, or will it be same instant for every observer? What do you think?
So for the inside observer, which who is in the calm, so it would be different for you.
I'm talking about the time. Like let's say it happens at 10 a.m. So what do you think that for the person in the helicopter will see at 11 or 10, or like before 10 or after 10?
Same time.
Exactly. Now time is something which has no relation to the frame. It's absolute in its sense. So we say that time is invariant. That is, its calculation is free from any notion of frame. Okay, so time is something which is invariant. It does not depend on which frame you choose to calculate. Or in other words, I can say that if you wish to calculate the time, you are free to choose any frame of your convenience. And in fact, we must choose a frame which allows us to calculate the event easily. And that is the essence of learning this chapter called relative motion. So why are we studying this chapter? If you may ask me, then I will say This will teach you the selection of a right frame to make the calculation easier. So instead of solving every question in the ground frame, we sometimes prefer not solving the ground frame, but in a frame which offers me a simple observation. For example, let's say you're in a car sitting on the rear seat. The car is moving on a straight line with uniform velocity. And in your hand, let's say there is an apple. If you throw the apple vertically up, what do you think? The apple will go back to your hand? True or false?
True.
Yeah. So now you're throwing the apple and it's coming back to your hand. So what is the path of the apple in your observation? Vertical, isn't it?
Vertical.
In your observation, what is the path of the apple?
Vertical.
Vertical? No. Now,
Sir,
imagine if I, yeah, imagine if I observe the same apple in the ground frame. What do you think? For any ground observer, is the apple moving up and down? No. Why not? Because when you threw the apple, you thought, okay, you're throwing upward. So you gave some velocity, V naught. But you never realize that the car is also moving right. So the apple is having already this velocity, which is same as car. So for any ground observer, the apple will have two velocity. And so the apple will travel this way. And when it is landing back to your hand, because you have also traveled forward by the same speed as that of the car, so you're always beneath the apple, no matter where is the apple. So when the apple happens to be here, you were actually sitting here. Maybe. So the idea is you always happens to below the apple. So you never realize that the apple is moving this way. Did you? No. So it's difficult to observe the apple path as seen by the person on the ground compared to when you see from the car itself. So now tell me which frame is easier to analyze the motion?
Ground.
Ground is easier. Ground
sir,
is
the
like
car inside the car.
because this is simpler motion. It's a vertical motion, it's a parabolic motion. So which one is easier to deal with?
Vertical motion.
And now what is interesting is that no matter which frame you choose, answer must be same because what I said, time is the invariant quantity. So let's say if someone is throwing with velocity v naught and it is moving with in a car, the first thing first, if you remember the time of flight formula for vertical motion, let's say in car frame, this is a vertical motion. And what is the time of flight? The answer is 2 v naught by g. But this happens to in the frame of the ground also. Why? So although it's moving this way, we know that the formula is 2 uy by g.
It does not depend upon it.
Yeah, and because it's not taking care of the vc, so it is still 2 v naught by g. Or if you say no, sir, let's say this is some velocity v dash and this is theta. So you will end up writing 2 v dash sine theta by g, but a v dash sine theta itself is v naught. No, the idea is no matter which frame I choose, the calculation of time is going to be invariant, and the entire purpose of learning this chapter is searching for the invariant. And in the search of invariant, we always figure out some interesting frame which simplifies the calculation. In fact, which simplifies the motion also. So it is always good to convert a two-dimensional motion into one dimension. And that is the entire purpose of learning this chapter. Like, can you search for such frame? So as we'll progress in this topic, you will come across various method of solving question. And what you will observe carefully, if you have the very careful, I mean, observation or very keen eye to see the things, you will realize actually that while solving, I will be picking up some interesting frame suddenly. And every time I'm solving question, I'm trying to solve in a different frame. And the moment I choose the frame, you will see that the calculation becomes quite easy. Like, and you see, we all will love to solve question in a straight line than on a curvy linear path, right? Because we are more comfortable with one dimension than two dimension. So it's like kind of, you know, the the idea is to convert every complex motion, which is a mostly parabolic, into a straight line motion by suitable choice of frame. And also you need to realize that the purpose why we are doing is because time is invariant. So the calculation of time, because it's invariant, we can choose any frame. But don't do the same thing for displacement, because it will change from frame to frame, and you are supposed to write the answer of displacement in actually in ground frame. So they will be asking you, if nothing is said, it means find the displacement in the ground frame. And the time, okay, time is time, so time has nothing to do with the frame. Now the statement that the time is invariant is true for Galilean transformation, or you can say the Newtonian physics, or you can say the classical physics. So what we are learning is called classical physics, physics as set forth by like Sir Isaac Newton and his predecessors like Galileo, Kepler, Tycho Brahe, and many more. Okay, but in the going forward, so maybe in the beginning of the 19th century, maybe end of, okay, yeah, end of 19th, and how to say this, 1900. So near 1900, what happened? A new guy came into picture who changed the course of physics forever, and you all know his name, Albert Einstein. Now he was the first guy who claimed this assumption incorrect. Which assumption? Time is.
Time is no.
So he said that no, you guys are totally wrong. He said that time varies from frame to frame. Oh, that was like a big heartbreak for all the physicists in the world. So what they were believing so far, that turned out to be wrong actually. So now we need to realize that how wrong was it? Like, what was the big mistake we made? And the answer came that the mistake only happens in the sixth place of decimal. I'm saying sixth place of decimal. Let's say if the car will hit, so the person in the plane, car, on the road, they will see the event differently, and the answer will change by sixth place of decimal. So does it matter for the real life, like for our life? No.
No.
For us, there is no difference, and therefore, even though the Einstein said time is variant, he said time is variant, not invariant. We will not be bothered about what he said. So we are totally safe in our assumption. Nothing can touch us. So the invariance of time, as proved and claimed by Albert Einstein, do not affect real life, but it does affect something called the subatomic world, the nuclear reactions, the motion of protons, electrons, muons. So the world which is very like at the core of the universe called the nucleus or the nucleons or the sub-elementary particles which is much inside the nucleus, leptons, gluons, gluons, quarks. There are various um, random things will come. Now in their world, these things matter a lot actually because they do not move slow. They move as good as with the speed of light. And because the light is moving at a speed of meter per second, so even a error of minus 6 seconds will lead to the 300 meters error of displacement, which is huge actually. And imagine if the two protons are trying to collide and if the error is 300 meter, will they collide? No. So what kind of accuracy we need? We need the accuracy of diameter of the. So we need to know that these two protons will collide only when this gap is less than their diameter. So this d
Two diameter.
is less than 2 or maybe 2 times of diameter of each particle. And this size is so small that we cannot afford the error of even trillionth of a meter. We cannot afford actually. So we need a precision beyond your imagination. And there we need to invoke the what Einstein said. So we cannot go beyond without Einstein theory of relativity. Now that is something fascinating. So in our world, we are shaped by this assumption that the time is invariant, no one can touch. So as long as we are talking about the macro world or the phenomena at large scale, the Einstein assumption will not shake our base. So Newtonian physics is still very much intact, nothing to worry about. In the micro world, things are very strange, and yeah, we need to worry about a lot. Okay, so you don't worry about. So still, we believe that time is invariant. And now, if you have understood the concept of frame and the concept of measurable or observable quantities, and if you have really understood the concept of time is invariance or variance of time or invariance of time, so now we are good to go with the concept of relative motion. So let's move forward and try to explore relative motion. So I'll start with the famous line: motion or rest is always relative. It means there's nothing called absolute motion or absolute rest. It's always a frame dependent definitions. Okay. That is, both are frame dependent. So both are frame dependent definitions. And finding the absolute motion is meaningless. Finding the absolute rest is meaningless. And we know that the various example you can say that if you are in a car, your friend is also in the same car. So both of you are at rest with respect to each other. So if one of you becomes observer and try to observe the other, you will see the rest. But both of you are in motion for any other observer in the ground frame standing there, or maybe in a car who is which is moving at different speed than your car. So that is idea. The motion and rest is always a relative idea. No? There is no absolute meaning to it. Okay. So now we'll see the kinematical equation in the relative context. So now we're going to derive the formula for kinematical equation in the relative motion. So imagine we have two particles, one and two. Okay. And both are in motion. So one is also moving, two is also moving. So
So
to
which
deal with
direction?
any random direction, we don't know. So let's create a some frame. What is frame? It's a mathematical setup. So when you define a frame, basically you define a coordinate system. And why do so? Because by doing so, we make sure that we can write some mathematical equation. I mean, without because this is a mathematical frame, so this allows us to write something in mathematical format. So frame, as I said always, that frame is a kind of tool which allows you to write something. And if there is no frame, then what will happen? Then you have to express everything in literature. That's the problem. Yeah, tell me.
Sir, how we will express in literature?
You will say that particle one is moving, and that's it. But that will not make much sense, right? So let's say, imagine this way. Let's say there is a person who never saw any car in his life. He is in the remotest place of some jungle, maybe some travel areas, maybe some Amazon forest. So what they have seen is only animals, and they have seen the how fast they move. So for them, the fastest thing that they have seen is maybe a tiger or leopard or some other animal, or maybe deer also. So now that guy come to a city. One fine day he comes to city. But what will happen? So if he comes to a city, he sees something called Ferrari, and then Ferrari just go pass by. How he is going to express his emotion?
Sir,
So
in
maybe
relative to the
yeah. So of course the Ferrari is moving very fast, and he has never seen such things like Ferrari moving in front of himself. So he cannot express the emotion. I mean, it's like he will be shocked, surprised, or whatever, but he cannot express how fast it is because how fast is a mathematical term, and that is why we need to define something called velocity or the speed so that we can express things in number, and then you can actually make sense out of number because brain is designed to compare numbers. Like we understand if you have taught me what is 1 2 3 4, and if I suddenly say you that 1,000, you can understand it's very far. So somehow you start creating the mental picture of 1,000. Okay, I don't know whether you are able to create or not, but at least your brain senses okay, it's big thing, something big. If I say million, then you understand okay, it's really big. Now if I say trillion, you know, oh my god, this is something tremendous. So we have billion, trillion, zillion, whatever. So number makes sense, and number is like a mathematical construct. So all numbers are again abstract notations. These are just a concept. Okay. Anyway, don't go into that. Okay, so one and two are two particles, and O refers to the ground frame. Let's say the origin is the ground frame. I'm calling it. So this frame I am assuming as ground frame, and it is also called the lab frame. So in American text, they use the word lab frame. In British, ground frame. Indian, ground frame. Okay, but in America they use the lab frame. That's how they have many labs. And now from origin, you join the first particle, and you call it position vector of the one. Now, of course, the position vector will not be same if they are in motion, so it will vary with time. Now that is fine. That is totally okay. But the question is not to observe things in ground frame. The two particles one and two. What happens if they start observing each other? Oh, that's interesting. So if one and two starts observing each other, now they are itself in motion, but now they are trying to see each other. So how the expression will look like? So first of all, we need to understand some notation, the meaning. So one R1 is representing the position vector of one with respect to origin. R2 is representing position vector of two with respect to origin, and one and two is called subscript. I hope you know this term, subscript.
Yes.
And we call it a single subscript notation. R1, R2 are single subscript notation. Okay. So now when we use the single subscript notation, it means by default the other observer is origin or the ground. So I mean this is something which is understood if I'm not mentioning explicitly. And so we know that okay, we are observing the ground frame. But now one is observing the two. So we denote by this. So if you ask particle one, where is two? How he will point his finger? If you ask one, where is two? The one will say it's there. This is the arrow representing what? What this blue arrow representing here? Can you tell me? What this blue arrow representing here? So you go and ask one, where is two? How he will point his finger?
All right.
Pardon? Hello?
Towards
So
y-axis.
towards
Okay, so if I say the left arrow, the left blue arrow, it is pointing whom?
Sir, 2.2.
Two. So what we write is this is the position vector of which particle? This arrow, the left arrow is representing position vector of which particle? One or two?
Sub
2,
Two. But who is saying this? One.
1.
Now origin is not involved, so we need to explicitly mention who is saying this. So we say R21. I mean the comma is not a nice way of writing. We just write R21. And we need to realize that now this is the position vector of 2 as observed by particle 1. And so now we can add the same thing for the other arrow. We can say this is the position vector of 1, and who is saying this? 2. So now from the single subscript notation, we have arrived at something called double subscript notation, and which is like a way to say that okay, now the observer is not the ground frame, it is some random frame, which may be also same as ground, like which may also be at rest, but now so far it's no longer the ground frame. Now this double subscript notation is something we are actually looking for. We are not trying to analyze the motion of two with ground or one with ground, rather each other's motion in each other's frame. That's the idea. So now what we'll go do is we are going to go back to the vectors. The triangle law again will be invoked. So from triangle law, what we can say? So using triangle law, what you can write? Tell me. So choose R1 and this one and this one. Then just choose these three. Don't take the last one. What we can write the triangle?
Sir, it's R1 vector plus R21 vector
Hmm.
uh, is equal to R2
Right. So we can say that R21 is how much? R2 minus R1.
R2 minus R1.
And that's obvious, that's easy, not difficult. So R1 plus R21 is R2. So we can say that R21 is R2 minus R1. So
Sir, what
now
R21? What is R21?
R21 is the position vector of 2 with respect to
1.
1. So the observer
Okay.
is 1
1.
and the object is 2.
2.
2 is the object and 1 is the observer. Object, observer. Think this way. So what is R2? Position vector of the second
2
particle
with respect to origin.
with respect to origin or ground plane. That's how you can think of. Okay.
Yes, sir.
Now similarly, can we also write? Yeah, we can of course write the other arrow, like instead of R21, can you take this one and this one and this one again? The other three mean triplet, ignoring the first double subscript. Now use the second arrow, this one. What we can write?
Sir, it's R2 vector plus R12 vector is equal to R1.
And so you can see that R12 turns out to be 1 minus 2. So now we are seeing two very interesting facts that when we have 2 1, then the difference is 2 minus 1. When it is 1 2, then it is 1 minus 2. So in general, I can say that if I write RAB, any random thing, then it will always have the meaning A minus B, no matter what. So now we have established the very first formula of relative motion. This is the first equation, the first formula you can see. So how the displacement is related? Of course, by difference of the position vector of each particle. Okay. So the double subscript notation is like when you switch from ground to the other frame. The first, the alphabet or the first thing which you write after the R is the object. The second one is the observer. So if I write R object and then you write observer.
R
This is
object
the
minus
formula. Yeah. So object means what you are observing. Okay, the thing you are observing, and who is observing. What and who. So what are you observing, and who is observing? So now this notation is not very difficult, or is it difficult? No,
no.
it's very easy. So R21 is how much? R2 minus R1. So what is R12? 1 minus 2. Okay. So now we can go faster, and we can finish the
Sir, I
answer.
want to note the last page. Hello, sir, noted.
So let's begin with the 2 1 only. So for rest of the discussion, I will keep this R21. So differentiating with respect to time. both side of 1 d by dt of r21. So d by dt of r21 is equals to dr2 by dt minus dr1 by dt, because we are differentiating. So on the right hand side, we know that this is called by definition velocity of each particle in the ground frame. So on the left hand side, we call it v21, and you can say this as a relative velocity of the two with respect to what?
One.
1. Now, this is not just a formula. This is something much more than formula. And now we need to realize something even deeper. So V21, like when one is the observer, the object velocity is not changing, right? So what we are doing is the object velocity is intact, and then you are adding something extra, which is minus V1, which means to find the relative velocity of any object for any given observer, you just add the reverse of your velocity to the object's velocity, which is already in place. So don't worry about much. And I think that is natural, isn't it? Why not natural? So let's say if someone is standing on the ground, I mean, if you are running a car, so in the car frame, how the object is moving? Backward. So if the observer is moving with velocity v1, then what will be the velocity of this object if it is at rest in ground frame? V1 backward, isn't it? Okay, I think you have not understood this part.
No.
If there is a road, there is a car, and there is a driver in the car. So you're, let's say you're driving this way. So now for any observer in the car, if the let's say there's a dog sitting on the road, in which direction the dog will appear for the observer in the car?
Opposite that.
Sir, opposite direction.
So if the car velocity is v1, then what is the velocity of the dog? Exactly v1, right? So if you think carefully, what this observer in the car has done. So this observer has added a velocity v1, which is same as his own velocity, but in the opposite direction, isn't it?
Yes.
In vector form, I can say if the v1 vector is representing the velocity of the car, then what is the velocity of the dog? Minus v1, and
Minus.
that has come from where? Because of the observer. Now imagine that the dog is already moving this way. With v2. So now the dog will have its own velocity as intact along with the v1. So now in the frame of car, how the dog is moving?
Horizontal. Oh, and slant.
Which is the resultant of these two, right? V2
Yes.
and minus. And that's obvious one, because why? Because in the, let's say if the dog is not moving, so the dog must be somewhere here after some time. And then if the dog is moving, then it must be somewhere here. So if you just combine these two effects, maybe you're here, the dog is going this way. So the idea is when we have an observer, then the observer velocity is added in the reverse direction. That's the idea, to find the relative velocity. So that idea is important, not the like difference formula. Like don't mug up like this, v2 minus v1. No, don't mug up like this. Try to understand this fact. What you are doing, you're adding the velocity of the object which is already in place, and you're adding one extra term. And what is that extra term? The opposite of the observer's velocity.
Sir, we
Isn't
are
it?
observing the dog from the car.
Yeah, we are observing the dog from the car. Now, what will happen to the dog? And if let's say dog is observer and car is object, if that is the case, then car will have velocity v2 downward and v1. So car is moving this way, and that's obvious because if the dog is moving this way in the one frame, the car will go in the other direction. That's easy. So this is the direction
Sir,
of
I
velocity
mean,
of car with dog, and this is the velocity of the dog with respect to car. Are you getting the point?
so what is the v2 velocity of that car?
The v1 is the velocity of the car, which is already there, and if the dog is running with this v2 velocity in the ground frame already, so the velocity of dog will be added to the car in the reverse direction. So if v2 is upward, then we have to add downward.
Minus v2.
So which means minus v2 is downward, right? The value is v2 only in the direction downward. That's the idea. Okay.
So,
Understood?
sir, if we add them both, then the sum will be
Yes.
like minus in
Yeah.
subtracting.
Yeah. So the addition is like the subtraction because you are adding a reverse direction, so it looks like subtraction, and that's the
Sir, and
only
if
idea. Yeah.
uh, sir, if dog is moving horizontally,
Mhm.
so along the yellow line only with some initial velocities are there.
And let's say car is moving faster,
Yes.
so the arrow of the car will be bigger, right? Now let's say you want to take the car as the observer, so dog will have two velocity, v2 forward and v1 backward. So what is the net of this? Net will be
v2 minus.
v1 as it, which is bigger one.
Okay.
So net will be left, and because this is bigger than this, so we are left with only this value in the backward direction. That's it.
And v2, and if v2 is also in the v1 direction, then v1 plus v2.
If let's say car is going this way and dog is running this way in the ground frame, now you want to make some one of them as observer. Which one?
Dog.
Okay, so now dog is the observer. Okay, great. So dog will see the car will have its own velocity intact, and then reverse of dog will add up in the same direction. It will add up in the same direction. So the net velocity is how much? V car plus V dog. It will add up
V
actually.
dog.
If I say V1, if I say V2, then numerically the car will go right with velocity 1 plus 2. And that's obvious because this is the rate at which they will separate. So in the dog frame, the car is moving faster with this speed, and in the car frame, dog will go backward with the same speed, faster. Okay.
Yes.
So it's very easy. Like we need to understand what is the V2 minus V1 is representing. It's the resultant of two vectors, and we have learned about vectors in chapter vector. So it's a resultant of two vectors in which the object velocity is not altered. We don't disturb that velocity in vector form, and we add additional velocity, which is the reverse of the observer velocity. It can be one dimensional, it can be in a different direction also, not to be always straight line. And the effect of these two will decide the overall motion of the object in that frame, the frame of the two. Now, this is the first step. This perspective you need to develop in your brain. Now, I'll keep this as equation 2, and now I'm going back to the third equation. So, what is the third equation? Differentiating differentiating equation 2 with respect to time. That's the idea. So if you differentiate equation 2 with the time, what will you get? D by dt.
Acceleration.
Acceleration.
Correct. So the left side we can call it as second. I mean the relative acceleration. We call it A21, and it is definitely A2 minus A1. Now this term is very interesting for one particular case which we will be anyway interested, and that is called the projectiles. In case of projectile motion, we know A1 A2 will be how much? It's G, right? The free fall acceleration is G. So for a relative motion of two projectiles, A1 and A2 will be always same value G. They cannot have different acceleration, right? So if you throw two bomb in air or two balls in air, will they have same acceleration or different acceleration? So irrespective of the fact how you throw, both will have same acceleration G. Understood? And therefore, what will be the relative acceleration? What is A21? It is always 0. It means when the first ball will look at the other ball, if you make one of the ball as observer, then that ball cannot see the acceleration because both will fall with the same acceleration.
Yes, sir.
Acceleration cannot be observed actually. And in fact, the vertical displacement will be like the displacement caused by the gravity, which is half gt square, will be same for both. So you cannot see the vertical jump due to gravity also, because you will always on the same level. Let's say you're falling from sky, so you will fall down, but you or both of this will be in front of each other if there is no velocity, because they are falling by same depth, same height, you can say, whatever. So for relative motion of two projectile, this is very famous expression. The A21 becomes 0. There is no relative acceleration. And again, I'm saying again, this is again, this perspective should always be with you. That is, every expression of a relative motion, like A21, which you write as A2 minus A1, it is always thought as the resultant of two vectors, one plus. So what you did for the velocity, the same thing you need to also apply for acceleration separately. Now you won't get questions, many questions in fact, in which A relative is also there and V relative is also there. Most of the questions will be very easy and you can solve actually easily. So in most of the questions that you will be encountering is that A relative will be always 0. So mostly it's a velocity dependent stuff. They solve using the concept of velocity. And again, it's a resultant of A2 and minus of A1. So if you know that A1 is this way, if you know that A2 is this way, so can you represent A21? How the A21 will look like? What is the vector diagram of A21?
Sir, the A21 will look like A1 is actually observing at A2, so it will look like the arrow should be towards the A1.
So the A1 will reverse the direction. That's the only thing is you have to reverse the A1. That's it. And because you reverse the direction, then the resultant of the A2 and minus A1 is the answer. So if I draw the parallelogram, and we know that how to draw the resultant from the chapter of it. And if you don't know, go and revise it. It's very important now for this chapter. So the pink arrow is the A21. Now this is difficult to realize. Okay. In fact, I would say that okay, you all drove on your paper, like try to get the feel of it, hang of it.
No,
So
sir,
draw on a
understood.
paper. Okay.
Sir, for this case only, like what you gave example that body is going like which has direction up and like it is oblique. Sir, for that only a1 a vector to one is zero vector.
Pardon?
Or for every sir, or for every situation it is zero a to one. It would.
It is only zero for this case.
Okay, sir.
Not for any other case. Or it is only true for case in which A1, A2 are equal. If the acceleration of two moving particles are always same, then obviously the relative motion will be the relative acceleration will be zero. What is the problem? Okay, so let's draw something like before we start the question. So let's say we have two vectors v1, v2. So v1, v2 is representing two velocities of two particles. Okay. So in the same diagram, can you plot v21 and v12 both? How the v21 will look like, how the v12 will look like. So draw the v12 and v21 vectorly using this two arrow. Can you do this?
Yes.
Go ahead.
Sir, V12 is towards the southeast direction.
You draw and just WhatsApp me. I want to see it.
So V21 now.
Both v2 and v12.
So V21 will show towards the arrow will be towards V2 and V1's arrow would be towards V1. Oh, sorry, V12's arrow should towards the arrow of V1.
Draw the v12 and v21 and send it to me on WhatsApp. I want to see.
Okay, sir.
Sir, thank you.
Correct. Both are correct answers.
Sir, I'm sending someone.
Okay.
Sir, I've sent it.
Yes, yes, that's correct.
So one question.
Yes.
So V21 and V12 are always in the opposite direction.
Pardon?
So V12 and V21 are always in the opposite direction to each other.
Yes, 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 yes.
So we
V12 is
can
actually, see, it's a common thing, no? When you write a V12, what do you write? 1 minus 2. If you take
yeah,
minus common, you can write as 2 minus 1.
minus 2
It is always V2. So V12 will be always opposite of V21. That's always true. And similarly, you can say A21 is always minus A1. Okay. So once you know one answer, the other answer we need not to calculate. It's always the opposite of the first, and that is good enough. Okay.
yeah, yeah.
So now let's say we have all the equations ready with us. So now we have to write the relative kinematics. Now writing is very tedious, but application is very easy. Okay, so let me write the relative kinematics for constant relative acceleration. So we write relative kinematics for constant relative acceleration. So imagine if the relative acceleration is constant, which means a2 minus a1 or 1 minus 2 or a12 or a21 or a1 and a2 are constant. You can send whichever way you want. So if every acceleration, if a1 and a2 are constant independently, it means that difference is always constant, right? So if I say a1 is constant, if I say a2 is constant, so the relative will be also constant, not a big deal. So in such case, how we write? In the first formula, so we write in vector form. Maybe I should write from here. Let me put this into box. This should not disturb our remaining expression. So let's say we write the v equals to u plus 8. Now what you need to write is just add a relative. That's it. It's easy. Or if you want, you can change it to v21, u21, a21. So now if you start with 2 1, then continue 2 1 throughout. But if you start with 1 2, then make sure that you continue the same. But you should not mix 1 2 with 2 1. If I write 1 2, then I will just maintain the order. You write the expression, and both will give you the same answer because the only difference is sign, which is maintained throughout, so to cancel out. So the idea is like we can add in either of the way we want, and if you want to expand, it's cumbersome, but you can expand. So final velocity of 1 minus 2. I'm just expanding this part is initial velocity difference like this. It is up to you. Now the next formula is uh, s equals to half a t square. So s equals to ut. So we write a relative, relative. What is s? It is r minus r initial. But this is again lengthy. Relative, relative. What is u relative? Okay, that's right. U relative. What is half a relative t square? And what next? So if you want to write in terms of component, you can say R12, the R not 12, the initial U12, plus half a12 t square. And then if you want to do it further, 1 minus 2, the final difference, the initial difference, if any, u1 minus u2 plus half okay, this is okay, not fitting.
So we can standardize it.
So what you are supposed to do is maintain the order. Okay. Now we will never add the third expression. Why? Because third expression is basically a scalar equation. It comes from the energy conservation. So the third expression, which we write v square equals to u square equals 2s, we can use that only for one dimension at once. So if you want to write the third expression, then there's no vector form, but there is a scalar form. So we can write as vx square equals to ux square plus 2ax x minus x naught, and then you can apply the relative for one dimension. Like you cannot do it for the two dimensions. So we can say vx square relative that's numbers. Then ux square relative to ax relative or no, this is x relative minus x not relative, but not required. This is we can do directly if needed, and of course we'll need center. So you can drop the this formula. You can just start to use plus. Let me make it simple. 2a s, I mean, and then you can think of a relative. But what is the caution here? That this is not a vector equation. This is for one dimension you can use. So the first two equation of kinematics is a vector equation, which you can use for 1D, 2D, 3D, 4D, whatever. And the second is only for one dimension, like the last expression, the third equation. And anyway, we will be dealing with the first two only. In fact, the equation which we use is the second equation. This is used most of the time to solve questions. Okay, but this is okay. I mean, this will never affect our learning. These equations will not something big. You can always do by the common sense. Okay, so we can actually apply the concept of kinematical equation in one dimension. But I will discourage it. Why I will discourage it? Because one dimension is like too easy case to go with the relative concept. You can do by common sense or by the ground frame method. So I'll show you some question which I will not solve in the relative motion concept. It's too easy to apply the big concepts. But when the question becomes really difficult, two-dimensional questions mostly, then we prefer solving in the relative frame. So we'll see that one by one. So first of all, so we call it chasing problem. So someone is chasing someone like my police and thief and all. So we have two particles, so maybe two objects. You can think of one as the police, other is the thief. And both will be moving in the same direction like this. So let's say the first particle having velocity u1 and acceleration a1. The second particle is having velocity u2 and acceleration a2. And imagine that let u2 is more than u1 and A1 is more than A2. Now, what does it mean? Do you understand this meaning?
The initial velocity of one is less than that of two.
Initial velocity of 2 is more. So, who will go ahead of whom?
So two will be first ahead of one, but after some time one will like
Yes,
chase the
after some time it will change now because of the greater acceleration, eventually velocity of the one will be more, right?
yes
At the end, one will be the winner, but in the beginning,
two.
yeah. So the idea is simple. So in the beginning, uh, two will be ahead for some time, but the one will have the last laugh. Okay. So
So
yes,
the theory part is over of relative
yes,
motion.
everybody is one. There is no theory. So all we have to do is the problems. In Now the problems actually very important here, and we have to learn various ways to think of a problem, solve a problem. Theory is nothing in this chapter. Theory though we already knew actually, and I just rephrase the theory in a relative form. So now the question is simple: after what time it will chase each other? Like, who will chase? So after what time the chasing will occur? So we know that when it will chase, they must be at the same position, right? So they must
Yes.
be one must be crossing the other. So the displacement of each particle will be same. So delta x1 is delta x2. So why we should solve in the Gramian relative frame? I can just directly write what I can write. What I can write. Delta x1 equals to delta x2. That's it. We know that answer, and this is happening at some time t. So t will be same for both the particles. So we can write as u1 t plus half a1 t square equals to u2 t plus half a2. Okay, so although this is the question of relative motion, but there is no need I'm saying. Just solve this and that's done. So 2 is more than 1, so bring 2 minus 1 into t equals to 1 by 2 a1 minus a2 into t square. And you can cancel 1 t because the initial value we know they were together. So the t comes out to be 2 u2 minus u1 by a1 minus a2. Now let's try to solve this in using the relative concept just for the demonstration that why we should not use. Now we got the answer. That's easy. Now using relative uh, relative kinematics. So okay, so how we write r like r minus. Oh, these are so many things we need to write. Okay, so although I'm writing for the sake of expression, nothing else. And see, I can write in one line. So I know what is r1. What is the final position of the first particle? Some value. And what the final position of second particle? Same value, but this value is zero actually. And they also started from the same point, so this is also zero. Do you realize this? So they meet, so the final position is same for both, and they begin at the same location, so both term comes out with zero over, so zero. And what about the first term here? So it's 1 minus 2 because one dimension. We don't have I and j component. So in one dimension, you can just remove the arrow and continue with the answer. Then we can add 1 minus 2. Done. And it's the same answer. If you solve it directly, you get the answer. So what is difficult in this case? To understand that this is same. And we are talking about the x coordinate, not the separation. So they have same x coordinate always. I mean, not always, sorry, in the beginning and in the final. So in the meantime, one may be ahead, other may be behind for some time. But eventually they will meet here and then it will chase after that. So in the relative sense, the expression we have to rewrite, but if you solve, it turns out to be same answer. It is always in fact same.
Sir, but V2 is greater than V1.
And you have to just follow the order. It will go on the other side, it will become negative, positive, and you can solve it. Not a big deal. So both will have same direction, so same velocity, isn't it?
Yes.
Understood? Okay. So now I'll solve one particular question which is of my interest
So I want to know the last one.
in one dimension. Yeah, you're saying something?
So I want to know that last.
Uh,
So can you just explain that once again, that
yeah. So
R1 minus
what
R2
is what is R1? You need to understand what is R1. Position vector of the first particle.
first?
What is R2? R2 position vector second particle. When at any time t. So when you're about to chase, both position vector will be same or different. Now
Same.
here the position vector will be replaced by the x coordinate because you are moving in x direction. Let's you can call it x axis.
So
So both will
understood.
have, yeah, both will have same x coordinate, and initially also they had same x coordinate, and so is answer. Okay. So now the second part is look at the situation. So let's say there is a road maybe, and there's a turning here, and now it's a big road. Maybe the narrow road, big and narrow. So okay, so there is a guy who is driving really fast. This is a car, and this car is moving really fast, dangerous. Okay, this is a light. Now it's night. Okay, so now the moment he turns, he realized that there is a car already here. Now this driver of this car is quite relaxed guy, maybe a octogenarian, and he's very much calm, relaxed. And now this car is driving with constant velocity v1, and he was moving very fast, as I said, v2. And the moment he turned completely, that guy realizes that, oh my god, now something is wrong. So let's say he's turning somewhere here, and just to show you the event. And because his light can reach this car, he realized, oh my god, there's a car. And the moment he realized this car is there, the distance between them was, let's say, the distance between these two cars is, let's say, d. Now d is the distance at the moment you realize. So the velocity at this instant is v2, of course. But now to prevent the collision, he applies the brake. Now which car? This car will apply the brake. So when you apply a brake, you develop a retardation. So you can say you will have an acceleration backward. It's the same way of saying retardation. But the car in the front will continue moving with the same speed v1. So question is, for what value of d, the minimum value of d, the collision will be prevented. So for what minimum value of d, collision will be prevented.
So V1 is moving constant.
Yeah, V1 is not doing anything. V1 is still continuing with the same speed because V1 is like, the windows are closed and they're relaxed. They know that nothing will happen. Okay, so driver will look forward, not backward, right? So who will try to prevent?
A call from Amit, Bangalore, Amazon.
Hello, sir.
Sorry, guys, just got a call from a very, very old friend of mine. Okay. So for what minimum value of collision do you, okay, are you calculating? Anyone solving this question?
So,
So what is given to you is AR is given, V2 is given, and V1 is given. And then you're supposed to solve it.
say yes. So using the first formula, we have to first find the time, and then in the second time, we have to put the time to find the v.
Yeah. So do it. So you think for a while, then I'll solve.
Sir, I got answer, but sir, it's very big.
Okay. Okay, let me solve this question. This is actually
So
okay.
first I calculated the time from that first equation, like
Okay.
v2 minus v1 is equal to u2 minus u1 plus a2 minus a1
Okay,
times
okay.
2.
I will tell you. What is first of all, tell me what is the condition to prevent the collision? What do you think that the car, which is the, let's say, car number 2. So to prevent the collision, the car 2 should be at rest or should be at some velocity. What is the idea of preventing collision? Like we need to understand the how you drive the car, like because that's very important. It's a very real event. I mean, this happens all the time for with every driver. So do you need to stop your car to prevent the collision, or what else you need to do?
So yes, we can be down.
So you have to slow down till your velocity becomes same as the velocity of the
The
front,
person in front of
right? So if V2 I reduce from V2 to V1, my job is done. Because if I can stop, not there is not to stop. If I reduce my or slow down my car till I attain the velocity of same as V1, I am saved. Because if both velocities are same, they will not hit. So the idea is before you complete the d distance, you must attain this velocity, isn't it? What is the idea? The car number 2 must slow down to the speed v1 before traveling d. No, that's the idea. And if that is happening, my job is done. Okay. So that is the essence of the v2 and v1. So how we can do this? So imagine, okay, let's say they hit each other. Now, if they hit each other, what does it mean? In time t, okay, in when they will hit is like v1 will be there or somewhere ahead. Of course, it will be somewhere here. So let's say the v1 is the first car is somewhere here, and the rear car is almost touching. I mean, just like this. and let's say this happens after time t. So I'm assuming the other way around. I'm saying that it hits the car after time t. So let it hits the car after time t. Now, if you are hitting the car in time t, it means the distance traveled by the first car in time t plus d must be equal to the distance traveled by the second car, isn't it? What is the condition
Yes.
for hitting? So in the time t, how much the first car will travel? I can say v1t. The the first car will travel v1t, and the d is the gap also. So the first car will go ahead by v1t. D was the gap. So these two displacement must be covered by the which car? Car number
The
two.
first
The second car.
second.
Second car will travel this much in how much time? The same time, because it's hitting. So we can write as v2t minus half AR t square, because it's a retardation. You're applying brake, so you will retard actually. And therefore, if you look carefully, which is difficult to you, it looks like a quadratic in time. So let me write
So
as
one question.
yes.
So why did you V2T minus? Why did you pick the
Well, I'm writing the formula of displacement of the second car. Right? Second car is retarding. So which formula you use for retardation? V2t minus half AT square, right?
yes? So the only A will come AR means retardation.
AR means R is the subscript for retardation. AR is the retardation.
So AR is equal to minus.
AR is a value. AR is the retardation value. Retardation.
Okay. Retardation.
So what is A? A is minus AR, right? What is acceleration? Minus of AR. Understood? So, okay. If you know, okay, no issue. So this must be the displacement of the second car. Let me write it down. And this we can write as ut plus half AT square. Now let's substitute the value. So v1t plus d equals to, what is u? For the car number 2, it's v2. That's the initial velocity. T plus half. What is a? Minus AR. Why? Because it's obvious, it's retardation. So what is acceleration? We write always, you remember, in formula A represents acceleration, not retardation. So we must write acceleration with minus sign. I hope this is clear now. No. It's still not clear. Is this clear, guys? Respond. Is this
Yes, sir.
clear? Okay. And now, if you convert it into quadratic, v1 t plus d. Let's go. Oh, I can write directly. So I'm writing directly. You can understand AR t square. This side, this side. Okay. 2v1 minus 2v2 minus v1. Now, if you rearrange it, look like this. I am taking v2 minus v1 because I know v2 is bigger than v1. So minus sign is there. So, okay, anyway. Now, this is the expression I'm getting, assuming they will collide. So T must have some real answer, T must have some real value, right? So now I want to contradict my assumption. What I will do? So to contradict my assumption, so what I can write? So to contradict my assumption, I will say that there is no real answer because I don't want to collide actually. I want to prevent the collision. So for no real answer, we know that discriminant of the quadratic must be negative,
Less than.
less than 0. So if you write so, b square 4v2 minus v1 whole square, b square minus 4ac, which is 8 ARD, is less than 0. And therefore, this will give you the answer d more than v2 minus v1 whole square upon 2AR. Now, this is the answer. To prevent collision, the d must be more than this value. And that is what we expect. That d should be even bigger than some lower value. So if the d is less than this value, you will hit the line. It will collide for sure. So now this is a really real life situation. And this question is a very, very old problem of Resnick and Halliday. So this question was published in somewhere in 1930s or 40s. It's so old, but still it's relevant today. Right? So we use this particular concept. Let's say AR is known to the device. Let's say if you are the Elon Musk and designing the driverless car, so in your code you must put this function. So camera will catch V1, V2. Camera can understand what is V1, V2. And the moment you see the D is approaching this value, you will start applying brake. Why? That is what you expect. Okay.
Yes.
So okay, these things are, of course, I mean, right now we are not going to code everything. But I'm saying that even these small things become part of a very big projects like driverless car. And everything we know, everything will follow the laws of physics. So what is most important is once you understand the physics part of any situation, then going to other field is very easy. To become a software developer or engineer doing some real world problems, it requires physics and mathematics, and therefore you need to be good with both. Okay. So although it looks like a very trivial problem of kinematics, but it's not so simple. So we have used mathematics, we have used so many things. Now, how we can solve using a relative concept? So let's try to invoke the concept of a relative motion to try to understand this particular question. So the idea is, if something like what is this? Yes. So this is the first particle. I'm going to just do a particle. So for now, you know what is the situation, and this is the other particle. And okay, this is the initial gap D, and this produces an acceleration backward AR. AR is the retardation. So because we always denote the vector as acceleration, so this vector is opposite to velocity because you are opposing the velocity. So that's the idea. Now to solve with a relative motion, you must take one of them as observer, and I'll prefer taking the card number 1 as the observer. So what is the V relative for the car 1? Or I can say, what is V12? Sorry,
V1.
V21, because 1 is observer. So if you think, I mean, logically, it's easy. Because
Sir,
V2,
it will be in direction of V2.
yeah, correct. Because V2 is more than V1. So the net will be V2 minus V1, but in the direction of V2 only. Right? Even if you subtract V1, V2 is a big arrow, but V1 is a small arrow. So what we do graphically, we keep the object fixed and we add the observer in the reverse direction. And this will be equal to how much? A net velocity of length this. So in the V1 frame, what is the initial velocity of V2? V2 minus V1. Okay. Okay, that's interesting. Now let's talk about the acceleration. What is the acceleration? AR. But there is nothing for the V1. V1 is not accelerating, so it will not contribute or change the acceleration. So it will remain AR1. Okay. Now, can you tell me what is the final velocity of the V2 in the frame of V1? So eventually the speed will slow down till the value V1. That's the idea, right? So when both will be moving with V1, so both arrow will be equal. So finally, V2 and V1 will be same, right? So eventually V2 and V1 will be same, and therefore what we can say, what is the V final? Like this is the initial actually. Oh my bad, there's something I made a mistake here. So I should change this so that. So this is U21, isn't it? So what is V21? It's 0. Why? But eventually both are moving with the same velocity, isn't it?
Sir, is it given information?
No, it's not going. Tell me how you are going to prevent the collision. If the rear car is moving with the same speed as the front car, will it hit? No. So to prevent collision, what is the rule? The car which is following or chasing must slow down to the velocity of the front car. Understood?
Yeah, sir. Sir, but they are moving in opposite directions. So V1 and V2.
How they are moving. This is a vector diagram. Come on. What we are doing here? We are adding the vector. If you remember, V2 minus what is V12?
V1 minus V2.
So it's a first vector as it is, and second we have to reverse, right?
Yeah, sir.
So the car velocity, this is the velocity of the car, rear car. Sorry. So this is in one dimension, right? So in one dimension, V1 is forward, and V1, the first car, the observer is also forward. So in the car frame, it is backward. No? How you add? Okay, you don't understand this. So what you were doing in the beginning, the addition, we are doing the same in one dimension. Understood? No, not clear. Okay. What is the velocity of the car number 1? V1 always, it is always right. What is the velocity of the car number 2 at the end? No idea. Okay, leave this part then. I mean, if you're not understanding, then you can leave. That is the good method. Okay, so you are not getting the idea of preventing collision. So I may put a note to prevent collision. The rear car must slow down to the speed of front car before hitting. Like if you can slow down, if you can slow down to the speed of the front car, then there is no need to worry about it. You may maintain some distance, and it just, let's say I apply the brake, and I by traveling here, my speed has become V1. So now there will be some gap between you and the front car, and this gap will not let you collide, right? Understood?
Yes, sir.
You are not understanding. See, we are applying the brake in the rear car, so it will slow down. And if it will slow down, then its speed will decrease. So I'm saying that decrease the speed of your car till it becomes equal to the front car. Then there is no question of collision, isn't it? Understood?
Yes, sir.
Good. So can we say the final relative velocity of the two car is 0? Can we say?
Yes.
Yeah. So now we can apply. Okay, I want to know how much you have traveled till you have come. Your initial velocity was this much. Now you are at rest. So how much you have traveled? So we can write as v square equals to u square plus 2s. Just don't write the relative, it's cumbersome. We know this is 0. We know this is 2 minus 1. We know this is 2ar because a is negative. And this is the distance you have traveled relatively. So I can just write s relative is how much? v2 minus v1 by 2ar. Now this is the distance which you have traveled. Now for no collision, the d must be more than s relative, isn't it?
Yes.
For no collision, d must be more than this, and that's the answer. This is equals to
Divided by 2.
yeah. So now this is the idea. This is how we think actually. So you need to do some practice. In one dimension, you can do. That's why I said in one dimension you can do the way you have been doing, just by ground frame. Don't try, or maybe you can try. But this should see, unless this is not coming intuitively, there's no benefit of this. Like I mean, if you go hard and fast with this method, and that's not good, because when we do the relative motion, first we need to develop the intuition, like how we can see the velocities, how events is happening, how event will look like if I change the frame, because that is the idea, right? We always change the frame to make it easier. So what I did here, I changed the frame from ground to the v1. Now this was my very much like a conscious decision to take v1. Why? Because v1 is not doing anything. So I thought, okay, let's go to v1 and take as a reference, and then analyze what v2 is doing. Okay, and we know that v2 is doing this much. So in the frame of v1, the v2 must come to rest. So when v2 will be come to rest in the frame of v1, it will come to rest only when the v2 is moving with the same speed as that of the v1. Then v1 will observe you to be at rest, isn't it? Now you take some
Yes.
time. Take some time, realize this, understand this, think about it, and then this will come to you naturally after some time. So don't worry. I mean, a relative motion will not click so easy. It is the most difficult part of kinematics. So it looks easy, but the chance of confusion is always there, and that will be cleared after some time naturally. It happens naturally. Maybe after 1-2 reading, you will get the realization suddenly. Oh my God, it was easy, but I was not getting it. So just wait for some time and let it happen naturally. Don't force yourself much. And if it is not coming naturally, keep it like this for some time. It will come, but just practice. So spend some time thinking about it. Okay. So now one dimension kinematics, one dimension relative motion. I'm ending here only because it's of no use. I'll go to the other dimension and we'll teach you something great, something very fascinating about relative motion stuff. So we'll see the fascinating stuff in next lecture. Okay. Till then, bye. Take care.